Today we wanna talk about the set of linear maps because we wanna say everything in the set theory language. Of course, our object linear map should be some element of a set. But moreover, we wanna say is that also I told that everything we wanna treat in the linear algebra is almost always a vector. So what I wanna say is the set of linear map forms a vector space. So the today's topic is to show that set of linear maps are in fact forms of vector space with some proper addition and S multiplication. The symbol for set of linear maps is because it is linear, we use LVW, or because we record a linear map is just a homomorphism, so we write hom VW, and this is set of map phi, which is phi v to w, and it is linear. So it is set of all linear map from v to w. Record that this is just class, so if we wanna say it is a set because of a separation axiom, it should be some subset element of something or a subset of something. In fact, record that map phi is a map, so map is a subset of a Cartesian product. It means that phi is an element of a power set of a Cartesian product. I need more space, so I'll move it a little bit right. Yeah, okay, again. It is just power set. So homomorphism, hom VW is the power set of V times W. Now I'll explain some other notion because we know there are many different homomorphism. For example, isomorphism is bijective homomorphism, and if V equals W, it is called endomorphism. So endomorphism, it is nothing but a homomorphism to itself. So we write and V for just hom V to V. And if it is isomorphism into itself, so it is V equal W, and also isomorphism, if this both are true, we call, maybe it is better to distinguish, it is automorphism. For automorphism, we use AUT V. It is subset of and V, or record that it is just hom V to V. So this is some just a notion, but today we'll focus on this notion hom VW. So we will use mainly on this. This is just extra. Okay, now our goal is to show that there is some proper addition and S multiplication for these linear maps. So what we wanna show is that hom VW and something addition as multiplication. Let us write some just plus box and dot box is a vector space. This is what we wanna show today, main goal. And then let us be more clear. V plus, let us write clearly, hat V be a K vector space. And similarly, we can write W plus W and hat W also K vector space. Then the homomorphism the addition should be, because our set is now home VW, it should be home VW times home VW to home VW. Similarly, S multiplication symbol, now this one is also, let us say this is K vector space, this is K vector space, so this is also K vector space. Then it is K times, is send K times home VW to home VW. Okay, then what is that? Okay, then for example, plus is defined like this. For or phi and psi both are home VW, then we can define phi plus psi. Yeah, this is now some operation. Let us say also there is some vector v in v. Phi plus v in v becomes phi v plus psi v, but phi v and psi v are both element of W, so this is summation in W. Similarly, for or A in K and for or phi in home VW, we can define A times phi, and also we cannot say something with just map because we don't know how to multiply map, so we need always some v in v. Then we can act v here because this is also, we assume that this is also element of home v, so now we can say we can act v here, but the result should be A times W phi v. So what we have is summation becomes W summation. This is very similar result from the linear map. So we have two different notions you need to check. So CF linear. In the linear map, okay, we can also combine this. If you have A times, linearity was such that A times heart V, V1 plus V, V2 becomes A heart W phi V1 plus W phi V2. So in linearity, you have summation and S multiplication in V. So domain summation and domain addition becomes target addition. Target addition and target S multiplication. But when we define vector space, it is different. You see the summation and S multiplication in the map, but still what they become is the target summation addition and target S multiplication. It is when you should be maybe not important, but I think I like it to compare these two. So now you have a clear definition, addition and S multiplication, which is well defined, and why they satisfy all the axioms, because W is vector space plus in W and S multiplication in W or satisfy vector space axioms, so we don't need to check again. Now we can do some other thing, so different thing. It is some side Cartesian product. Oh, sorry. So now I wanna talk about Cartesian product of vector space. Because we define some set theory notion from the union of set. We define union of vector space. Unfortunately, it does not vector space. And intersection of set gives intersection of vector space. Similarly, we can do the Cartesian product of set, because what is Cartesian product? It is V1, for example, V1 times V2 is the set of V, some ordered pair V1 comma V2 with V1 in V1 and V2 in V2. So we choose each one of element and make some ordered pair. It was the definition of Cartesian product. So we can have for the, let us say V1 plus 1, maybe let us skip V heart 1, and similarly V2 plus 2 and heart 2. Okay, let us be more general. Vn plus n heart n. So let us say these are all K vector spaces. Because from the set, we can define the Cartesian product of the set. So V1 times V2 times Vn. This is a Cartesian product of the set. What is it? It is just, let us move up a bit left. This is not just the thing that V1 ordered pair Vn and V1 is in V1, and finally Vn is some Vnth element. So just making some long list of ordered pair. So it is simple. I think you know what it is. But this is not our goal, because our goal is always not going just to set. Our goal is to make some vector space. Then what you need to do is find some proper S multiplication and addition. So what is our goal? Our goal is that V1, Vn, and some plus and some S multiplication. I want to show that this is also vector space. This is what you always wanna check first time. So then, of course, plus should be, I don't wanna write domain. This, I just write some bracket, and S multiplication is K times, okay, I always forget to write K vector space to be clear. V becomes something, and all the thingy, this is V1 times Vn, V1 times Vn. Okay, I write it V1 times Vn, V1 times Vn, V1 times Vn. This is what we want to find, and what you want to is that these two things should satisfy all the vector space axiom. But one more thing, we want this plus and S multiplication not randomly. We want these guys come from these guys. Then how to do it? We can just simply write plus as something like that. So for all, let us say A in K, and also for, let's write U1 UN and also is in V1. Yeah. U on UN in and V1 that Vn is in V1 times Vn. So we have some ordered pair and some number, and we can define u1 plus u1 comma un, this is one vector, plus u2 v1 dot vn, this is another vector. The result is that u1 plus, but this is summation on vector space v1, so u1 plus v1, and u2 plus 2 v2 dot un plus, this is in vector space n, summation vn. So we have ordered summation if we recall it, and also a hat v1 dot vn equals a hat 1 v1. Why we do this? Because what we want, okay, let me first try dot a hat n vn. Why we do this is that, recall that we want these guys from these well-defined, so these guys are, we know these guys are given, and this, from these green guys we want this S multiplication and addition uniquely, unambiguously well-defined, and this is what we have. So now we have proper addition and S multiplication, and of course these guys satisfy all the vector space axiom because each green guys are satisfy vector space axiom. The whole set should satisfy. If you don't believe, you can check, but I don't want to check. Okay, this is, so now what we have proven, we have shown that this is true. This is really, Cartesian product is also really a vector space. And because it is Cartesian product is just some making ordered pair, you can find the dimension simply. Dimension of, for example, v times w is that. Now, if it is like other case, we call v is k vector space. But in here, you are assume that there is S multiplication and addition. Similarly, we call, for example, this is k vector space. It means that we assume there is a addition and S multiplication defined like this. And because this is k vector space, we can see dimension of v times w. But it is simple because it is ordered pair. We can say that it is dimension of v times dimension of w, because it is some v times 0 plus 0 times w. So maybe I should write here this one first, because sorry for making wrong direction. What we can say, we can say v times w as a vector space thingy if this is, if there is some set x as subset in this we want to say, I want to say this is v o plus w, but there is one assumption. This cannot be defined randomly. This has some assumption. If we write this, it means that v is some subset of some, let us write some x, and w is some subset of x, because the why we write this, because this plus and union and intersection. These all operations are maybe union we don't need because the unions are not interesting. Plus or just plus or what was it? Intersection. These are all defined in subspaces in between. So we cannot say, but because we can say that simply V is subset of V times W, and W is V times W subset. From this is true and this is true, so we can write this. So really V times W is V O plus W, but I think it's good to remember that in this you have assumption that V and W are vector space of something, and this something might be just a Cartesian product or more bigger one. Anyway, then we know dim of V times W. The dimension is dim of V O plus W, and this is dimension of V plus dimension of W. So now we have some relation between Cartesian product, dimension of Cartesian product, and dimension of each vector space. I do this because I think you might confuse between dimension of home VW, because recall that dimension of home VW in the definition you might be confused. It is a subset of power set of V times W, so it should be smaller or equal to 2 times because power set dimension is 2 times dim V times W. This is just 2 times dim V plus dim W. So this is what we have, and in fact, dimension of home VW is the multiplication of them. How to show this is simply you can choose because dim V means that if it has n, it has linearly independent n vectors, so we say have some EI and it's a basis of V, and we have some WI. Want to let us say dim W is M. Not to introduce more letter, we might write this one way. Then last time we showed that there is direct there is isomorphism between them for the linearly independent WI and EI, and so we can choose n basis, so we have some phi EI becomes WJ. Each EI and WJ, there are dim V choice and dim W choice, so we can relate them as mentioned. How many ways we can relate them? This is just this way. That's why they have this dimension. And yeah, this is the story about the homomorph set of homomorphism or set of linear maps. So what I wanna say today, the main topic was just not this one. Yeah. Today main topic was that home VW is a vector space.